Hey, so we've been looking at our voltaic cells. Now we can start to diagram what's going on in our two different chambers at the anode and the cathode. Our next step is to talk about the why. Why does this actually happen, right? We know it happens. We can measure this electrical energy, but the question is, why does it do that? And so the reason why our voltaic cells work is because this reaction is spontaneous. We know the electrons want to go from the anode to the cathode. That's because our different materials, usually our metals, tend to give up or attract electrons at a different degree of attraction. I like to think about it kind of like electronegativity. We know certain elements or particles attract electrons better, and it's the same type of principle. We know if we got different nuclear charges, different degrees of attraction for those electrons, we can get them to go from one species to the next. And by splitting it into two parts, we can send it across an external wire to do that. And so it really is looking at the ability for our metals to do this and get those electrons to flow through the circuit. We already know that that means that the delta G would be positive, but we need to introduce this new unit of measurement, and that's our cell potential. It's describing how well our battery actually produces electricity, the potential electrical energy available to do work. We call it E cell, and it's going to be greater than zero for a spontaneous reaction, just like delta G. If your E cell, if your cell potential to make electricity is greater than zero, it's going to be spontaneous. It's going to want to go. And we do need some units for that, for our new kind of unit of measurement here. And our unit is the volt, going back to that volta that we saw earlier this unit. And by definition, 1 volt is just 1 joule of energy per coulomb, which is a charge. We're going to talk about that later this unit, but just know that the units are volts for these kind of cell potentials, and you'll be good to go. So what are we talking about here? What is it that we're really describing? And so when we look at our cell potential, we're describing how well the electrons want to go from the anode to the cathode. And we give that a term. We call it the electromotive force, or EMF. This is really kind of the vocab term we use to describe how much our electrons want to go from anode to cathode. But it's a lot like electronegativity, and the trends are kind of similar as well. E naught is standard conditions, right? So standard 1 atmosphere, 1 molar. So E naught cell is our quantitative measurement of the tendency of our reactants to proceed to products at their standard state conditions. That would be 1 atmosphere of pressure if it was a gas, 1 molar solutions, and everything's at 25 degrees. And so for this picture over here on the right, we're looking at our kind of zinc to copper. This is the one we built in class, right? If everything had been standard, we should have pulled a voltage of 1.10 volts across our electromotive force, or across our cell. That's assuming everything was under standard conditions. Mine weren't, but that's okay. We didn't come quite out at that 1.1. But we call this the standard cell potential. Here's this E naught, or the E naught for the cell, for the whole thing together, describing how well the electrons are moving from anode to cathode. It's the electrical difference. Really, we're describing how well does one container want to give the electrons away at our oxidation side, or anode, how well they want to give them away, versus how much our cathode wants to gain them. That's really what we're describing. We're just talking about their attraction here. And so the tricky part here is we're going to have to kind of break away from the number of electrons or the number of particles, because really we're just saying, if I got 1 particle of copper, how well does it attract? If I had a mole of copper, well, it's going to have the same degree of relative attraction. We'll talk more about that here in just a second. So really, it is going to depend on the ease of reduction at the cathode versus the ease of oxidation at the anode. If you really want to give them at the anode and you really want to take them at the cathode, your E cell is going to be really, really big, very, very spontaneous, because we know the electrons are going to want to go. The smaller that difference becomes, the less spontaneous our reaction, and the lower our cell potential will be when we actually measure that voltage across our wire. Cool. Again, though, good news, we stand on the shoulders of giants when we start to look at some of these very pre-established and well-established kind of values. For your common alkaline battery, we talked about these briefly as a spontaneous reaction. They pull 1.5 volts when we measure that difference in voltage. For your car, it's 2 volts. For your standard kind of the little button batteries, those are 1.3 volts. Electric eel comes out at 0.15 volts. And then for squid, 0.070 volts. Very, very, very low for that nerve ending in our squid. Just there's different voltages. Don't need to know these. Know that there are different voltages depending on what you're doing, but we use these a lot. There's a lot of practical applications when we start to look at our cell potentials. And yeah, there's a lot of data out there. When you come back to class, I'll get you a sheet that has all these cell potentials on them. I believe there's also a chart in the back of the textbook. Don't worry, we're gonna look at these. But really what this means is we have some values. We got some numbers that describe how well we want to give or take electrons. Now you'll notice all of these are written as reduction potentials. So essentially what we've done is we've created this chart that describes reduction as the gaining, right, of electrons. We're saying, here's how much all these things want to gain electrons. And this makes sense. You know that lithium and sodium don't want to gain their electrons. Fluorine and chlorine, they do want to gain electrons. So there's some relationship to electronegativity again there. And you'll notice there's this red one here in the middle. That's hydrogen. And that's kind of the standard. We actually measured all of these potentials against hydrogen in the other chamber. So essentially we've set the scale to hydrogen. Here's how much, for example, fluorine wants to gain electrons compared to hydrogen is essentially what this is. So that's why hydrogen gets the special red. It's the 0 point that we set the scale to. And so we can actually use these numbers. We can start to actually calculate then, given what's in the two chambers and who wants to gain and who wants to lose, we can calculate what the cell potential would come out to be. Let me hide for just a second. And the good news is the math is pretty straightforward. We're just gonna add them together. So here we got our E naught cell. So we're saying what's the total cell potential? And that's gonna equal the cell potential of the cathode plus the cell potential of the anode. Kind of adding together how much we want to gain and lose these electrons. Now, the tricky part here is kind of watching the sign. So if we're looking at this first reaction here, nickel and our magnesium, split it into your two half reactions. Start with your oxidation numbers. We know this is starting with 2 plus, 0 for the magnesium, nickel's going to 0, magnesium's a 2 plus. We picked a nice easy example for sake of introduction. So our nickel's going from 2 plus to 0, it is gaining 2 electrons. Our magnesium is going from 0 to 2. It is losing 2 electrons. Okay, so if we're thinking about what's going on here at the anode, remember that anode is oxidation, right? For our anode, our oxidation losing of electrons, right? We know our magnesium is gonna turn into magnesium 2 plus, magnesium 2 plus, and kick off 2 electrons. At the cathode, or the reduction reaction, half reaction, where we're gaining our electrons, we know our nickel 2 plus is going to gain 2 electrons to turn into our neutral nickel. And so we need some values. We want to know how well does magnesium go about losing them? How well does our nickel gain them? Well, we go to our tables. So we go to our table and we find our two half reactions. Well, we'd find nickel fine. We'd find it just as it's written. They're all written as reduction reactions. And so we'd say that the E for the anode from the table, E naught standard for the anode from our table, we just look on our value. I've got negative 0.23 volts for that one. But if we go to the oxidation side here, it's not written that way. In the textbook, it's written as Mg2 plus 2 electrons turning into magnesium. And that has a cell potential. So for that reaction, E naught would equal, let me look at my text real quick, negative 2.38 volts. Well, okay, well, we know this is how much we're saying this wants to gain it. Well, if we flip the reaction just like in Hess's law, well, the E naught for our anode then, sorry, anode, I miswrote over here. Sorry about that. This should be for the cathode. This should be for the cathode. Sorry, working fast. So cathode was that negative 0.23. Didn't have to do anything for that because it was already a reduction potential. For our anode, then we would just take this value and we would flip the sign. We'd say, well, it actually, if we're talking about how well it wants to get rid of those 2 electrons, it's the same attraction. It's just reverse, the same amount of energy. It's just flip-flopped. It becomes positive. Well, okay, then for this reaction, if we want to know what the total is for the cell, we would just add those 2 numbers together. Don't have to worry about the 2 here. That has no effect. If you had to multiply anything to get it to balance, has no effect. It's just these 2 values. added together. So for our E naught for the total cell, it's going to be our 2.38 plus our negative 0.23 volts. And when you plug that in your calculator or run it in your head, you should get 2.15 volts is the total cell potential given these two kind of anode and cathode cell potentials. Come back in class, we'll get our data sheets, we'll look at a bunch of examples, we'll make sure we're feeling comfortable. I really just wanted you to kind of get the info you need so that we can start running with these calculations when you come back on Thursday.